plus b is equal to 0. So sorry, negative RC. So b is equal to negative RC, whatever the value of R and C are, right? So that was very easy. So now we know this is equal to 1 over S minus RC divided by 1 plus SRC. Okay, so this is our capacitor voltage, okay, in the S domain. Now, do we know how to take the inverse Laplace transform of this one to find capacitor voltage in the time domain? Of course, this one, it's in the form of K over S. So that's just basically like a constant, right? If you take a derivative of, if you take the Laplace transform of a constant, you would have 1 over S. Actually, the most correct way of writing it is just a unity functions, which is like 0 before t equal to 0 and 1 afterwards. And for this one, it's, if you remember, this was e to power negative alpha t. If you take Laplace transform of that one, it would be 1 over s plus alpha, right? So actually, if I divide this by RC, this would be also 1. Okay, now, so this is now going to be e to power negative alpha is 1 over RC, so it's going to be negative t over RC and times e of t. Okay, so our time domain response is basically this. So instead of taking integral, taking derivative integral, solving differential equation, we found the transfer function of our system. We found the Laplace transform of our input. Then we found the frequency domain response, which is the output in the frequency domain. And we took the inverse Laplace transform of that one to find the time domain response. So that's what the advantage of Laplace transform and transfer functions are. So this is one example that shows that. Just another example, very easy example, just a review of your electric circuit knowledge. We have an RLC circuit like this, right? We want to find the impedance of this circuit. What is the impedance? It means like what is something that if I multiply by my frequency domain current, it would give me the frequency domain voltage. Okay, so that's going to be very easy to figure out. Z of S is basically V of S over I of S. And we found the impedance of all of these elements. So this is going to be basically R plus LS. It's in parallel with 1 over CS. Okay, so this is basically 1 R plus LS multiplied by 1 over CS divided by R plus LS plus 1 over CS. Okay, let's multiply the whole thing by CS. So in the numerator, we're just gonna end up with R plus LS. In the denominator, I'm gonna move the terms a little bit. it's going to be LCS2. I multiplied this one by CS plus RCS plus 1. Okay. So this is like a second order transfer function because the denominator's order is second order, this one is first order. We always find the maximum order, which is this one, so this is a second order system. This is one way of showing the transfer function. In many textbooks and in many problems, the standard form of transfer function is shown where the coefficient of the highest order term is 1. So if I divide everything by LC, both top and bottom, like the numerator and denominator, S2 plus this one divided by LC, it's going to be R over LS plus 1 over LC. This one is just going to be R over L. Let me just write this one as LS plus R. This is now divided by LC. It's going to be 1 over C times S plus R over LC. We call this one standard form. Standard form of the transfer function. Okay. So that was just an easy example just to show you what the transfer function is. So the general form of the transfer function in the examples that we see here are in the polynomial format. So let's say that we have a plant, we have a system, and the general form of it, we're going to have two polynomials, numerator, denominator. Let's just like do this one, ASN plus BSN minus 1 plus blah, 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 plus KN. This one, alpha S power M plus beta S to power M minus 1 plus dot, 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 KM. Okay, so the order of the numerator is nth order. For this one is mth order. And the order of the transfer function order is maximum of m and n, right? So for the previous example, the numerator was first order, the denominator was second order, so we say that that transfer function is second order. And this is like how we write polynomials, but if I want to write this in the standard format, I have to divide everything by alpha, right? So we're just going to end up with something like this. S to power m beta over alpha S to power m minus 1 plus km over alpha. And we'd have to do the same thing for the numerator, b over alpha S to power n minus 1 plus km over alpha. This is the standard format, okay? The polynomial form, this is the standard form. In this course, we deal with real systems. And for most of the systems we see